Hello! A couple of weeks ago, NASA announced that they had accepted Blue Origin's bid to build the next lunar lander, which will be called Blue Moon, effectively tasking Blue Origin and the whole national team with not only building said lander, which by itself is already a big enough problem to solve, but also with solving the issue of successfully storing cryogenic propellants for long periods of time in space. And the same is true for SpaceX. Cryogenic propellants are used in spacecraft and rockets due to their high energy content. The usual suspects include hydrogen, oxygen, and methane, which must be stored at extremely low temperatures to remain in a liquid state. Now, the storage of these propellants in space represents several significant challenges, the biggest one being their storage over extended periods of time, ranging from months to years. The main issue here is the extreme temperature difference between the cold propellant inside the tanks and the relatively warm temperatures that the exterior of these tanks can reach. And it's not that space is warm, but rather the temperatures that are needed for the propellants to stay in liquid form are extremely low, and in and of itself, these temperatures are extremely difficult to maintain, a fact which will further be aggravated when you have a star next to you constantly applying a cozy layer of heat on top of your tanker spacecraft. So oxygen needs to be at around minus 183 C to not boil off, which is not too far off the minus 162 degrees Celsius that methane needs. And this similarity in temperatures makes it easy to store both liquids close to each other. Hydrogen, on the other hand, needs to be at minus 253 degrees Celsius to also remain in liquid form. Now, one of the many advantages of being down here on Earth and having an atmosphere above us is that we have this wonderful thing called convection, through which the air sort of takes away much of the heat emitted by objects. However, in space there is no air around, so all the heat accumulated in any object can pretty much only be emitted back into space through radiation. In the Blue Moon lander's design, we actually see at least two big sort of flappy radiators. So what happens is that if the liquid propellants warm up too much, they slowly begin to boil off into gaseous form, which will have to be vented out, and this results in a valuable loss of fuel and oxidizer. Especially problematic here is hydrogen due to the extremely low temperature it needs, and also how small the atoms are, which will almost always find a way to leak out when transferring them from one vessel to the other. Now, there are ways to reduce propellant boil-off. Back during the Apollo missions, the insulation employed in the third stage of the Saturn V rocket was polyurethane foam attached to the interior side of the tank wall, and this insulation managed to bring the percentage of liquid hydrogen boil-off during the 3 hours that the spacecraft spent coasting in low Earth orbit down to about 1 metric ton, which still was an acceptable margin of under 10% of the total amount of liquid hydrogen remaining for the second burn. Now, during the Apollo missions, such a high boil-off rate was acceptable because the amount of time that the hydrogen needed to be stored was merely the hours between burns. However, for the purpose of storing liquid hydrogen for months on end, a 10% boil-off rate every 3 to 4 hours will completely empty your tanks in less than 2 days, so that's obviously not an option. And this continued to be a problem during the shuttle era. Roughly half of the liquid hydrogen purchased to fuel the space shuttle's 3 main engines was lost due to boil-off. The storage tank where NASA kept its liquid hydrogen, which had been operational since the times of Saturn V, was vacuum jacketed with 3-foot thick perlite insulation, but still boil-off remained an ongoing problem and substantial losses were considered unavoidable. Now, I'm not sure whether this tank still is operational because last year NASA finished the construction of a new tank for storing liquid hydrogen. This new tank can not only store about 50% more hydrogen, but is also able to cut off the boil-off rate by roughly 50%. Thanks to a new glass bubble insulation method that replaces the perlite used in the older tank, and so bringing down the amount of lost hydrogen to around 0.03% per day. Additionally, an equally new refrigeration system has been also integrated into the tank, which, once operational, will provide removal of heat energy using a heat exchanger together with a cryogenic refrigeration system, somewhat similar to what happens behind our refrigerators at home, although slightly more powerful in this case, and this is meant to eliminate the need to constantly vent hydrogen that has evaporated because this new system can supposedly eliminate boil-off altogether. Now, if this works on the ground, you will obviously want to explore the possibility of using this same technology with depots of liquid hydrogen and other cryogenic propellants in space. Plus, if you come up with a means of shielding your storage tanks from the sun and other smaller heat sources like Earth itself, similar to how the James Webb Space Telescope does it, then space becomes a really cold place. So this will definitely be an interesting topic to watch play out, not only with the Artemis moon landers, but also with other private missions that SpaceX will want to do, and Blue Origin as well, and later on for missions to Mars. Artemis 3 will land near the south pole of the moon, and there are craters there that haven't seen any sunlight in like ages, and so the extremely low temperatures inside these craters could actually make them excellent places for storing any kind of cryogenic propellants for future moon colonies or something. So yes, the main issue with long-term propellant storage is boil-off, with liquid hydrogen being the most problematic. Now, a second issue derived from boil-off, but that is more specific to being in space, is the zero-gravity environment, which adds additional complications. In terrestrial conditions, liquid propellants settle at the bottom of the tank, but in space they tend to float around in the absence of gravity, complicating the fuel extraction process. Also, while on Earth, any gas bubbles that form due to boil-off would rise to the top of the liquid due to buoyancy, and so the gases can then be vented out safely. However, in zero gravity, these gases will stay where they form, and as a result, these bubbles can accumulate throughout the liquid fuel, further complicating fuel extraction and potentially leading to inconsistent or unreliable propellant feed to the rocket engine. Now, if any bubbles are accidentally ingested into the rocket engine, they can cause combustion instability or even damage the engine. So this is one of the reasons why it's so important to maintain cryogenic propellants at their low temperatures and minimize or eliminate boil-off in the first place. And here is the cool thing: during the Apollo missions, NASA came up with the ingenious idea of venting the hydrogen that had been evaporated at such an angle that it generated enough thrust that the propellants were settled at the bottoms of the tanks where the engine intake is. At all times during the orbital coast phase, the upper stage of the Falcon 9 rocket achieves the same effect after a coasting phase by firing its RCS thrusters shortly before engine ignition. Now, the presence of this small upward G-force also ensures that the boil-off bubbles that form rise up so that they can be vented out safely, while at the same time also making the engine ignition safe. But whereas the Apollo approach managed to avoid dealing with long-term cryogenic fuel management due to the short mission duration, which allowed for higher boil-off rates, any kind of modern long-range mission will have to reduce the amount of boil-off drastically, or rather eliminate it altogether for this to really work out. So I hope you learned a thing or two about cryogenic propellants and how hard it is to tame them. I certainly did learn a lot. And with that, I thank you for watching, and I'll see you soon again. Take care. Bye bye.